What the heck?
Tagon.
Alright, so I'm going to solve a problem that I posed on my Instagram account, which simply asks, can one justify that these two things, these two expressions, this polar function here and this rectangular function here, are they actually asymptotic to one another as x gets smaller or gets more negative, or as theta gets closer and closer to 0? Either way, that's going to be the way to think about it here. And the only way we can really do this is to put both of them in terms of the same kind of coordinates. And it turns out, for me at least, the easiest way of doing this was to leave this one as is and convert the second one into polar coordinates. For a brief review, if we have a point in the plane, x comma y, and here is the origin, then this is some y component and this is some x component, and there's some angle theta there. We know that the radius r, the distance between the origin and the point xy, is going to be the square root of the quantity x squared plus y squared, and of course the angle theta is simply the inverse tangent of y over x. Now we're not going to need this aspect of it because we're simply going to be comparing theta as a variable, so we don't really need to put it in terms of x and y. Now that we've gone over this little review of converting from of rectangular to polar coordinates, we're going to apply that reasoning to this function here and see that these two things are actually asymptotic as theta gets very small. So, from those polar coordinates, you can derive quite easily that y is simply equal to r cosine theta, and from those polar rules that we just went over, you can easily derive that y is equal to r sine theta, and x is equal to r cosine of theta. So I simply have to replace it wherever I see it. And now we're going to divide both sides by r cosine theta. Of course, when we do that, this one goes away, the r's cancel, and we're left with sine over cosine, which is of course the tangent of theta. And this is equal to what remains on the right, which is e to the power of r cosine theta. Now we simply take the natural logarithm of both sides, and we get that the natural logarithm of the tangent of theta is equal to r cosine theta. Now, much like in this polar function, we have r, this is linear in r, and r is a function of theta. We're going to want to do the same thing here. So we're going to divide both sides by the cosine of theta, and we see that we can now represent the original rectangular function y equals x times e to the x as the polar function r equals the logarithm of tangent of theta over cosine theta. Now that we have both this and this in polar form, we can compare the two and see that they are in fact asymptotic to one another. How do we prove that something is asymptotic to another thing? Well, we want to show that as x approaches a particular value, that is, we want to show that as x approaches that particular value, whatever it is, that the ratio of those two functions approaches 1, or perhaps that the difference between them approaches some finite quantity. In this case, it's going to be easiest to compare them by dividing them and seeing that their ratio approaches 1. So the first function that we got from the second function that we got from y equals x times e to the x in terms of polar coordinates was simply the natural logarithm of the tangent of theta divided by the cosine of theta. Now, we want to compare the two in the sense that we want to see that their ratio approaches 1, so I'm also going to divide this expression by the original function that we had, r equals logarithm of theta. Now, the top being the logarithm of sine over cosine can be expressed as the logarithm of the sine minus the logarithm of the cosine. Now, what are we doing? Well, in the picture we see that theta is approaching 0. Now, if theta is approaching 0, then that means cosine of theta is going to be approaching 1, right? And if cosine of theta is approaching 1, then the logarithm of the cosine of theta must be approaching 0. And what we're left with is the logarithm of the sine of theta divided by the logarithm of theta. Now, of course, by the fundamental theorem of mathematics / engineering / who gives a crap, sine of theta is equal to theta. It's very, very close to theta for small theta, and so as theta goes to 0, this is going to approach logarithm of theta over logarithm of theta, which of course gets closer and closer to 1, which means that in some literal sense, the polar graph r equals logarithm of theta is in fact asymptotic to the rectangular graph of y equals x times e to the x. I hope this was a nice little puzzle for all of you to solve. Thank you for attempting it if you did. It wasn't too difficult. I just thought it was kind of an interesting curiosity. I'll have a full-fledged video coming either later this week or next week, and I thank you for watching. Have a wonderful whatever day it is. Bye-bye.